In this lecture, we're going to review some basics of uniaxial plasticity. Now, this being a class in fatigue analysis, we're not going to have any cyclic loading yet, but we'll get to that pretty quickly. In order to do cyclic loading, we really need to have some understanding of what goes on in monotonic loading. So let's make a note of that here. We'll do monotonic loading first, and then we'll get into cyclic loading. So by monotonic loading, what I mean is if we looked at stress versus time, we're simply starting at zero load or zero stress and ramping it up with time, and we're not decreasing the stress. We're not having any kind of cyclic loading or unloading of the material, although we will talk about unloading shortly. Alright, so there's different ways to express the stress strain curve of a material, and the most basic way is with what we call engineering stress and engineering strain. Now, the engineering stress is going to be defined as the instantaneous force divided by the original cross-sectional area. And the engineering strain is defined as the change in length of some segment of that bar divided by its original length. If you're in this class, I'm assuming that you are fairly familiar with the engineering stress and strain. Well, if we take a typical material, maybe like an aluminum alloy, and we were to load it up, there would be an initial kind of straight line relationship between stress and strain. This would get a little curvy. We might hit a peak, and it might drop from the peak, and then finally break or fracture over here. The highest point on this curve is known as the ultimate stress. With the S denoting the engineering ultimate stress for that material. The place where it finally breaks, that's not quite as important for us, but that would be the engineering fracture stress. There's different ways to denote that, but we'll use the symbol S with a frac for fracture. And again, that would be defined as the failure force, or the force at failure, divided by the original cross-sectional area. Okay, so again, just kind of review what goes on at a tension test. You have some sort of gauge length of material that has some initial length, and it has some initial diameter, which gives it an initial cross-sectional area, A0. These are important terms to know, and again, I'm assuming that you're fairly familiar with these already. Now, for the next graph, I'm going to take a look at a kind of a zoomed in picture of what happens here. I will point out that the graph that I just made for an engineering material, this is more of a cartoon than it is something to scale. The slope of the stress strain curve is usually very steep for most engineering materials, engineering metals in particular. They're very stiff. So if you were to plot this to scale, this would be very nearly along the axis until a certain point, and then comes over here. I do have some test data that I can share with you later, but again, I'm assuming that you've had a class as an undergraduate, probably in Mechanics of Materials Laboratory, where you've taken a data from a tensile test of a metal. Okay, so again, we're going to look at the initial portion of the stress strain curve. Maybe it looks something like that. Again, engineering stress and strain. The initial slope has a special name for most metals. That's the modulus of elasticity E. Some people call that Young's modulus. And it's the slope of the stress-strain curve when it's a straight line. There's a certain level of stress here that was called the proportional limit stress. And that is the highest point that you get on this curve where you still have a fairly straight line. Most metals have this kind of behavior. A lot of non-metals do not have the straight line relationship necessarily for very long of its stress-strain curve. So this modulus of elasticity then we can define as the change in stress divided by the change in strain when we're less than the proportional limit. So a lot of times I'll just show this as a capital E here. Alright, now there's another term that is a value that's very near the proportional limit stress, and we can define that as a yield stress, and in particular we define something as a 0.2% offset yield stress. Okay, it's kind of a mouthful to say, but it's really pretty easy to understand, I think. The 0.2% offset refers to a strain level. The strain level of 0.2% is the same thing as 0.002, whatever strain, unitless strain measurement units you have. So inches per inch or millimeters per millimeter. And by offset, that means that we offset our axis over to here. And with this initial slope of the stress-strain curve, following that dotted line up to the blue curve, that intersection point is the 0.2% offset yield stress. Now what does that mean? Well, a yield stress means it's the point on the stress-strain curve where we start to have permanent deformation. If we go back and think about our paperclip at the beginning of class, when we took that paperclip and opened it just a tiny amount and let it go, it went back to its original position. There was no permanent deformation in that paperclip. When we opened that paperclip up a lot, then we had some permanent deformation. We would have exceeded the yield stress. So if we want to say, we can define the yield stress as the stress level at which we have permanent deformation. Now here we run into kind of a quandary when we do our uniaxial tensile test with monotonically increasing loading over time. How do we know when we have permanent deformation until we actually measure something and see that its dimension has changed? And if we just start to have permanent deformation, how much precision do we need to have in order to determine the amount of permanent deformation? Is it 0.1 inch? Is it 0.01 inch? We can keep putting zeros in front of that until we can get to a teeny tiny number that we might have trouble measuring. And the other point is if we're in a monotonic tension test, we just throw it in the testing machine, not literally throw it, but we place it in the testing machine and we load it until it breaks. We are never unloading it until it hits its ultimate stress, and then the loads begin to drop. But that's a different situation. We're not trying to unload and measure the specimen every single chance we get. We're just going to pull it until it breaks. So the 0.2% offset method is a way for us to kind of estimate where we would have permanent deformation in a particular material. Some materials use a 0.2% offset, other materials might use a 0.5% offset. So it kind of depends on what field you're in and what kind of material you're looking at. But again, it's just a way to give us an idea of when we begin to have permanent deformation. So you should know those values. Let me make a new page. So we've been talking about our engineering stress and strain. We said that this engineering stress was the force divided by the original cross-sectional area, and we said that the engineering strain was the change in length divided by the original length of some gauge length of our bar when we test it. These are not the only stress and strain measures that we could use. You're probably familiar with already true stress and true strain, and we'll define those in just a minute. We're going to use different symbols in this class. We're going to use the symbol sigma for the true stress, which is the force divided by the instantaneous cross-sectional area. And for our true strain, we're going to use the symbol epsilon, which we'll explain in just a moment. If we look at a certain length of material from its original to its instantaneous length, if we integrate dl over L, which we get a natural log of L over L naught, we can define that as the true strain. So why do we use two different values, two different definitions of stress and strain? Well, let's think about what happens to a material when we stretch it. So if we have a bar and it has some original length and it has some original diameter, which gives us an original cross-sectional area, when we pull on it in tension, the bar gets longer, but it also happens to get skinnier. It changes diameter. So it has some, I should probably call that A sub I, it has some instantaneous cross-sectional area. This is when we put a tension on it. And it has some instantaneous length. So when we said the engineering strain was a change in length divided by the original length, that's not really accounting for the gauge length getting longer each time. And the true stress then would be something that accounts for the area getting smaller each time. It's really hard to see this in a piece of steel. You can see it sometimes in a tension test. It is really easy to see this if you take something like a rubber band and you pull on it. You can really see the cross-sectional area decreasing, or the width of a kind of a flat rubber band decreasing substantially. So there are good reasons to use true stress and strain instead of engineering stress and strain. The good reasons are when you are at relatively high levels of strain. So if we were to plot both the engineering stress strain curve and the true stress strain curve, they would initially look very much the same. This being our engineering stress strain curve. And our true stress strain curve. Initially, they're pretty much the same. These lines are supposed to be drawn on top of each other pretty much, but they begin to separate as we get near above the yield stress and near the point of instability or necking, which occurs at the ultimate stress. Now what I mean by necking is that initially, in the beginning, before we get to this ultimate stress, the material gets longer and it gets skinnier pretty much uniformly along its length. But when we get to the point of necking or instability, we have a very pronounced kind of a dent that forms. Oh, that's a bad drawing. Let me see. We get kind of a dent that forms in the material. That's called a neck. And you have a complicated state of stress there. You really don't have uniaxial state of stress anymore. But then that's what causes the load to decrease, causes a decrease in the engineering stress strain curve, comes down from that peak. And yet, if we calculate the true stress strain curve as the force divided by that small area, the true stress strain curve continues to rise until fracture because the area keeps getting so much smaller. Even though the force decreases, the area decreases faster than the force. So there's a couple terms that we can also define here. At this point, we can call this the true fracture stress. Let me write that in red to go with this curve. And what that is then is the failure force divided by the very final cross-sectional area. And again, the important thing to point out is that when we're at low loads, the engineering stress strain curve is pretty much the same as the true stress strain curve. At low loads and low levels of strain. Well, when we're above the ultimate stress of the material, there's really not a whole lot more we can do to that material. And so beyond that point really isn't very much concern to us. But there is a certain point. Now this point may map over to a spot over here somewhere. A little bit shifted over and up. There is a point though before we get to the ultimate stress and we're not down at the really low levels where there is a significant enough deviation from the stress strain curve, the engineering stress strain curve and the true stress strain curve, that we may want to take things into account. So what we're going to do next is we're going to take a look at some relationships between the true stress and strain and the engineering stress and strain for kind of this region right here that I'm kind of circling with my pen. So let's look at a few terms up until instability, up until the engineering ultimate stress occurs. So again, I'm just going to draw our little piece of material. Our gauge length initially is little l naught and has initial diameter d naught, initial cross-sectional area of a naught. We put some force on it, we make it stretch out, we make the diameter shrink a little bit. We have L and D and A for the new terms here. Our true strain term, what we said was it's the Ln of natural log of L over L naught. And our instantaneous length we can think of as being the original length plus some change in length delta L. We do have our engineering stress-strain relationship, that the engineering strain is the change in length divided by the original length. So if we want, we can express this line as L naught plus E L naught and so that means then that our our true strain can be expressed as L naught of L naught plus E L naught divided by the original length L naught. If we divide this through, we have the ln of 1 plus, I got a little carried away with my L naughts. Let's add one more step in here. L naught plus delta L is the instantaneous length, but we can express the delta L as E times L naught. It's the same as what I had written. It's just I don't want to skip a step here. Now I'm going to divide through by L naught, and I have 1 plus E. Alright, so we can have a relationship between our true strain and our engineering strain by this equation right here up until instability. That means we have a uniform strain distribution in our bar up until that point. The true strain epsilon is equal to ln of 1 plus the engineering strain E. Alright, now let's look at another situation that we might have. We're going to assume the conservation of volume for this next step. Now, is the conservation of volume a good assumption to make? Well, it depends. If you are in the elastic range of the material, the answer is no. That might sound a little bit weird, but when you have low loads, the atomic structure, the crystal structure of that material is such that those bonds between atoms of the material get closer together, and you have a change in volume. It's a very tiny change in volume, but you do get a change in volume. However, when you have plasticity, and we're looking at the portion of the stress strain curve where we're past yield but we're not quite to the ultimate stress yet, when you have a significant amount of plasticity, it's been shown through numerous experiments that the volume does tend to be conserved or very nearly conserved in those situations. So as long as we have enough plasticity, then this is a good assumption here. So what is that volume when we start off our test? Our initial volume is the length of that cylinder times the area of the cylinder A naught. And the volume during the test, we could find the same way. It's the new length times the new cross-sectional area. And what we're saying is that the V naught and the VF are about the same. Then we have this relationship that L naught A naught is equal to L times A. Let's work with this equation just a little bit. Let's rearrange this. Let's see. Let's divide both sides by A and then we're going to divide both sides by L naught. So we have this relationship right here, that the original area divided by the instantaneous area is equal to the instantaneous length divided by the original length. And so in that point of view, again, for large enough strains, our true strain can not only be expressed in terms of a natural log of L over L naught, but can also be expressed as a natural log of A naught over A. A naught over A. We have to be a little bit careful here. Don't just write A over A naught because of this relationship that we have. It's actually A naught over A. Well, let's take a look at stresses. We have our engineering stress, which is the force divided by the instantaneous area. By the original area. We have our true stress that's equal to the same force divided by the instantaneous area A. So there's a relationship between engineering and true stress. We can say that the true stress is equal to, let's see, if I rearrange this, I can say F is equal to S times A naught. So here we have S times A naught, that's the force, divided by the area A. Let's go back and look at our strain again. The strain is the Ln of 1 plus the engineering strain E, and that's also equal to the Ln of A naught over A. Then if we take the antilog of both sides, 1 plus the engineering strain is approximately equal to A naught over A, or sigma is equal to the engineering stress S times 1 plus E. Okay, so there were some assumptions that we made in this, but this is a good formula to use to relate true stress to engineering stress in a certain range of applicability. Sigma is equal to S times 1 plus E. There's not a whole lot of difference until E gets kind of big. With these equations then, we can measure an engineering stress strain curve, and then we can get, up until here, a true stress strain curve. And the reason why we're sometimes interested in true stress strain is because with significant plasticity, that's a better term to use typically than the engineering stress and strain. I will say that you really have to be careful and understand what's being used if somebody gives you some data. So if somebody gives you some data, whether it's a monotonic stress strain curve or hysteresis loops, just be super careful about how they defined all these terms, because it can make a difference in your values. All right, now at this point we will talk a little bit about unloading. We're not going to put the material into compression, but we're going to take a look at a situation where we could have stress versus time such that we're increasing our stress to some peak and then we're decreasing our stress back down to zero. We're going to take a look at the stress strain response of our material. And by material, I'm usually meaning a metal at this point, since we talked about doing metal fatigue analysis in the beginning. And we're going to be at some level that's above the yield stress of the material. So we have an initial straight line portion of our stress strain response. we yield our material, we get to this peak. That corresponds to the same peak level of stress right here. And so we're at a point what I'm going to call sigma and epsilon. Here's our modulus of elasticity, E. Now something interesting happens when we unload most metals when we have exceeded their yield stress. There's some things you think might happen. Maybe this just goes all the way back down straight line like this. Maybe it does something weird, but all we're going to do is we're going to take the load off. And what we find when we do those kind of experiments is that the unloading curve looks something like this. In fact, it has a slope that goes the same as our initial slope, the modulus of elasticity, and we unload down to this point right here, which is zero stress, and we have some residual strain. And for reasons that'll make sense real soon, I'm going to call this point epsilon sub p. Okay, so when we had the stress, we were up here. And when we don't have any stress, we are over here. Okay, this P stands for plastic strain. What it represents is the permanent deformation in the material. I'll go back to my paperclip example. If you take a paperclip and open it a little bit, it springs back to its original shape. You're less than the yield stress. If you take that paperclip and open it up a lot, like the 45 or 90 degrees, you might notice that when you let go of it, it doesn't stay at 90 degrees, but it springs back just a little bit. It might be at 85 degrees. Okay, what that is saying is that there's definitely some plastic strain, some permanent strain after the load is removed. But when the load was applied, that's this point up here, this strain epsilon is a combination of permanent strain and elastic strain. That's called the total strain. So I'm going to put a subscript T here. So the total strain epsilon T must have been a combination of some strain that recovered plus some strain that was permanent. The recovered strain is what we call the elastic strain, and that would be this amount right here. And again, I'm exaggerating this cartoon so we can see what's going on in the sketch. Oftentimes the elastic strain is a very tiny number. And the plastic strain isn't really big either, but depending on how far above the yield stress we get, the plastic strain can be many times greater than the elastic strain. So we define the other term. Let's define this. I could probably do a little better job of writing that word. That's the recovered strain. Okay. So again, the total strain is composed of two parts. How can we calculate any of that? Well, the elastic strain is related to the amount of stress that we have in the material. The elastic strain can be calculated by Hooke's law, which says that the elastic strain is equal to sigma over E. Maybe another way you've seen this written is sigma is equal to E epsilon. Let me put the E first. Okay, remember this is a straight line. The equation of a straight line is equal to y is equal to mx plus b. Well, there's no intercept since we think we start at 0, 0. And the slope is the modulus of elasticity, and instead of x and y we're using sigma and epsilon. So this relationship is nothing more than what we call uniaxial Hooke's law. So another way we can say that we have the total strain then is the total strain up at this point is our stress divided by the modulus of elasticity while we're up here, this stress value right here, plus some amount of permanent strain. Now here's the interesting thing. Take an aluminum. Almost all alloys of aluminum have pretty nearly the same modulus of elasticity at room temperature, somewhere around 70 gigapascals, okay? 10 million psi. Different alloys behave much differently beyond the yield stress. So they may have the same value of plastic strains, but different alloys of aluminum can have wildly different plastic strain behaviors. So here's something that's often done. We can take our stress strain curve and subtract off the elastic part of the strain. Let me make a new page. Okay, so watch my axes. I'm trying to be real careful with this. We have sigma on this axis, and now this is just the plastic strain. And the plastic strain we get by rearranging the total strain equation. It's the total strain minus the elastic strain part, sigma over E. And if I haven't been clear enough already, we are talking about uniaxial loading. Okay? So when we have zero stress and strain, obviously we have zero plastic strain as well. As we move up this curve, we don't hardly get any plastic strain until after we've yielded. So a lot of times I will show this curve that looks like this. Now is this exactly zero until we get a certain level of stress? Well, it could be. You might just have such small plastic strains that they're really negligible. How do we describe this curve? Okay. As I said, different alloys may have different behavior after the yield stress. So one alloy of aluminum may have a curve that looks like this. Another alloy of aluminum may have a curve that looks like this. It's a lot steeper. Another alloy of aluminum may have a curve that kind of looks like this. It flows more easily or it flows less easily, and there could be a range of the values that look like this. Okay, now at this point I'm going to ask you to read a paper by Ramberg and Osgood. Let me see if I can find it. Okay, this is on our class box account, and I know this is really hard to see right here, but I do like to show this first page because it's kind of interesting. We'll get to see the title here in a second, but notice this says restricted and then it says classification canceled. I always thought that was really neat. This was a classified document back in the 1940s, and it's the National Advisory Committee for Aeronautics, NACA, N-A-C-A, which was the precursor to NASA. And this paper is titled The Description of Stress Strain Curves by Three Parameters. NACA Technical Note 902 by Walter Ramberg and William Osgood. And, briefly I can read through the abstract or summary. A simple formula suggested for describing the stress strain curve in terms of three parameters, namely the modulus and two secant yield strengths. Dimensionless charts are derived, and they talk about different aluminum and stainless steel alloys. Let's kind of flip through this and see if we can see anything interesting here. They give us a formula, and notice it's got some coefficient and some exponent. That's the important thing I want to take from this. Not necessarily the exact form that they're using here, but notice that there's the elastic strain part, the S over E, and then there's the plastic strain part, which is this, that has something to do with some coefficient and exponent. Okay, Here they call a K and there's an N. And I know I'm flipping through this real fast. They go through and they do some nice analysis. Here's a steel. You see the kind of upper and lower yield stress value. Here's some very nice stress strain curve data points. I remember back in 1942 or 45, whenever this work was done, they didn't have computer data acquisition systems, so they had to do this very carefully with either hand measurements or they might have had some sort of a charting mechanism. And here's the stress, here's the strain, and here's some interesting plots. And now here's a log-log plot. Okay. All right. So I would like for you to read over the Ramberg Osgood paper. And let's talk about what it amounts to. Okay, so we're going to read it. So if you take the plastic strain, which is the total strain minus the elastic strain, and we showed that on a curve of stress versus plastic strain, it looks something like this, you know, and we showed the different high and low values that you can get. If you were to plot the log of the stress versus the log of the plastic strain, you get kind of an interesting behavior. We take a few data points. Remember, these are tiny numbers, much less than 1. You get approximately a straight line on a log-log plot. Now in a class in plasticity, I will give you some tensile stress strain curve data and you will deal with that, and you will find a fitting parameter. You will find what's called the slope of this curve, which is N, and then you will take and you will extrapolate this on a log-log scale out to a strain value, a plastic strain value, where the log of that number is 1, maybe it's over here, and that corresponds all the way over on this axis, running out of room a little bit here, corresponds to an intercept of a value called K. And this is a power law model for plastic strain, and the equation, the way it would be fit, again for stress versus plastic strain, is a power law is a coefficient K times the plastic strain epsilon P to the N power. When the plastic strain is equal to 1, anything 1 to any power is 1, then sigma is equal to K. Now the way that we would typically use this in our class would be to solve for the plastic strain. If we do that, then first of all we divide through by K, and then we have an exponent 1 to the N. So we would solve for the plastic strain, which would be the stress level divided by this material parameter K divided by, to the 1 divided by N power. And what Ramberg and Osgood did is they look at a variety of materials and say, hey, this fit seems to work for a lot of materials we're interested in. We use the modulus of elasticity, and well, we got to use 2 more material parameters, K and N, to describe what happens after yielding. Now the names of this, K is called the strength coefficient, and N is called the strain hardening exponent. Put it all together, we have our total strain relation. We have epsilon is equal to The total strain is equal to the elastic plus the plastic. In terms of stress, the total strain is equal to sigma over E, the modulus of elasticity, plus sigma over K, the strength coefficient, times 1 over N, 1 over the exponent. And this equation is kind of interesting, and I would encourage you to make a plot where you vary the K and the N values but keep the modulus of elasticity the same. And what you'll see is, below the yield stress, you use sigma is equal to E epsilon, so they all have a straight line. But you can model all the way from a perfectly plastic material to a range of hardening values. Okay. And the way these work is, if we go this way, that's kind of a decreasing N, and to go this way, that's kind of an increasing K. It's not necessarily unique. You might be able to find a K and an N, two different values that happen to give you similar looking behaviors. So I do want to emphasize that this is a curve fit. So they're curve fit, and I'll put this in quotes, material constants. So I need the quote around the constants. Maybe a better word would be material parameters. There are material parameters that can help us describe what happens after the yielding of the material. Now, the reason why we're interested in those kind of values in this class is when we get into strain life fatigue analysis, we're not as interested in infinite life fatigue behavior, but finite life fatigue behavior. There are a lot of interesting engineering applications that involve finite life, where we have some significant amount of plasticity. Okay, so we want to describe what happens to the material when we've exceeded the yield stress, and this is a very nice, useful, simple model. It's not the only one, but it's the one we're going to focus on in this class. So please take a little time and read that formerly classified paper on a curve fit called the Ramberg-Osgood relation.